pressure on hydrostatics. How to calculate the hydrostatic pressure distribution in a reservoir. My name is Hubert Chanson from the University of Queensland. Today, we are going to review the key question. What is pressure? What are the units of pressure? How to calculate the hydrostatic pressure in a reservoir? What is pressure? Pressure is the ratio of a surface force to the area of the surface. For a constant force, the pressure will increase when the surface area decreases, as illustrated on this sketch. Ultimately, for a very small surface area, the pressure becomes the derivative of the surface force or pressure force with respect to the surface area. What are the units of pressure? Pressure is expressed in Pascal, named after the French mathematician Blaise Pascal, who lived during the 17th century. A Pascal is equal to a Newton per square meter. Other pressure units include the bar, for example, used in meteorological and weather applications, on meter of water, a unit sometimes used in hydraulics laboratories. The pressure may be expressed as an absolute pressure or a relative pressure. An absolute pressure is always positive, with its lowest value, 0, corresponding to an ideal vacuum. On planet Earth, the atmospheric pressure would correspond to an absolute pressure of about 10 to the 5 pascals. Most of the time, we will use relative pressure, and we will often use the atmospheric pressure as our reference. And in this case, P equals 0 in the atmosphere, or at the surface of the reservoir that we see here on this photograph. Two key properties and features of pressure are: first, pressure applies normal to the surface. If we looked at the reservoir with a dam wall in the background, the water pressure of the reservoir will apply perpendicular to the upstream face of the dam wall. Secondly, pressure is the same in all directions at a given location. Pressure is a scalar, and this property is also called Pascal law after Blaise Pascal. Now, let us consider a water reservoir at rest. We will use as notation small d, or the depth of the reservoir, and z as the vertical elevation, positive upward, with z equals 0 at the bottom of the reservoir. The first key feature of the reservoir is atmospheric pressure at the water surface, P equals 0, when Z equals D. And in the reservoir, the pressure is hydrostatic, and the vertical pressure gradient equals minus rho G, where Z, the vertical elevation, is always positive upward, rho is the water density, and G is the gravity acceleration. The sign minus reflects that the pressure in the reservoir increases as we go deeper into the reservoir. The water density is typically about 1,000 kilograms per cubic meter, with values for both freshwater and seawater shown here, with seawater being slightly denser than freshwater. In comparison, the density of air is about 1.2 kilograms per cubic meter. The gravity acceleration is about 9.8 in Australia, but it varies around the planet Earth. Coming back now to our reservoir, the pressure gradient, dP over dz, is a constant typically, hence the pressure distribution will be a linear line with P equals 0 at the surface and P equals rho GD at the bottom. That is, we have a triangular pressure distribution as illustrated on the right-hand side of our sketch. And at a known elevation Z in the reservoir, the pressure will be equal to rho G d minus Z. So in summary, pressure is a scalar. It applies normal to a surface, and it is the same in all directions at a given location. We may apply it to hydrostatic to understand and calculate the pressure in a water reservoir with a hydrostatic pressure gradient equal to minus rho G on the pressure at an elevation Z in the water reservoir being equal to rho G d minus Z. All these are fundamental concepts to fluid statics and may be relevant to a large reservoir like here, like Thetana in Tasmania. Relevant bibliography include a number of textbooks, as well as some video movies in the same YouTube channel. Thank you for listening.